Okay, so the first part starts with the post-tensioning. Talking about the post-tension bridges, I mean box girder post-tensions. So I put them in the three main categories. The first one would be a single boxes. As you can see here, we have one single box where the slab and the webs and girder all are together, working together. And then we post-tension, and those post-tensioning tendons go through the webs and also the flanges, as you can see in the first images in the top. Then we may have the multi-cells. So we can, instead of like having a single box, we could have I mean 2 or 3 boxes, and you know, it could be wider, give us a wider area as well, and there are some benefits with that. Also, you can have multi-cell boxes like what you see in the bottom right here, and this type of bridge is actually not very common in all over the US. In some areas like California, they mostly use these wide multi-cell boxes. But anyway, this is a type of bridge that you know, could be post-tension, and it needs some, you know, certain type of treatment. So we're gonna discuss about them. So coming back to the post-tensioning, there are actually different construction methods for building these post-tension box girder. So I listed a couple of those here, and we're gonna quickly talk about those, and you know, seeing the advantages or, you know, benefits of each one at this time. First one is the incremental launching method, where you have these launching nodes going span by span, and then we construct the bridge, as you can see in these the diagrams down here. All right. By the way, I got these images from a VSL system, so just noting them as a reference. There are different options. The second one is the balanced cantilever bridge construction method, where you know, the bridge starts from a pier, and then from both sides we are adding the segments. It could be adding the segments, or it could have those moving the scaffolding and then go through, and then the bridge will be constructed, and finally they can you know, meet at a certain point. So I have an animation which I prepared from Midas Civil for you, showing how the construction sequences happen. So at each time that we are adding any segments, so we add a post-tensioning part to you know, to sew these segments to the constructed part, and finally we come up with the final model. All right. So we have another method also for the span by span, when you know, could have that main tower back there, and simply can add the segments to each other and post-tension them, or put them all together and then finally post-tension them. All right, so this is an segments that they selected. These segments is mostly, these type of segments are mostly used in span by span methods. So for incremental launching, these cantilever boxes, so they are mostly smaller piece of the segments. All right, so another method is a movable scaffolding system, where you can just have those scaffolding, and then goes goes through as far as the certain part of the structure is constructed, so it moves forward, and you know, builds the boxes over and over. All right, so in the second part, let's see how we can handle those type of bridges that we just talked about. So what I have here is a single span, a single box segmental bridge, and how did I model it is using a spline model. So the spline model is one of the common approaches that Ashto asks us to do when we have you know, segmental bridges or post-tension boxes, because simply we can simulate the entire structure as the entire superstructure with one beam element, and apply the loads, any loads that we have, post-tensioning loads, any truck loads, winds, or anything, any type of load that we have, we can apply it on this structure. But the point is, when we model them with the spline model, we just get the, I can say that we can get the global results or global, let's say, bending moments on this, but we can't get the all details. For example, we can't really study the shears in each segment, or for example on the abutments or on the supports, we can't get the shears in this area. So we may need to move forward and model the structure with different approaches. This model, the spline model, could be used both for a single boxes, single cells, or multi-cells. That's possible. But the point is, in the following slide, I will talk about the when the bridge become, when the number of the cells increases, and then we have wider segment, wider bridge, then we cannot really use the spline model. Let me just bring it up. For example, this one. When we have, let's say, 10 cells, then the bridge cannot be modeled really with one single beam, because then the structure is not really, one single spline model cannot model all the behavior of the structure. For example, if you have a moving load running in this side of structure, we might have a very large displacement at the other end if we go only with the spline model, because it's going to rotate it and go so much up. So that's not a really proper modeling. One approach that is available for this type of bridges when we have multi-cells is to discretize the bridge into smaller pieces, like what you see here, these vertical lines. So these vertical lines can technically separate the bridge or discretize the bridge to smaller I-shaped girders, like this is one, this is one, this is one, and then these sides are actually separate one. Then we can apply the post-tensioning tendons on those, and model them with the grillage approach. To understand this method better, so I can just show you this diagram. So in these diagrams, you can see on the left side, entire the boxes are modeled only with one beam. But as I said, if we have, we can't really model the behavior of the structure because, it's pretty wide and it doesn't work as a single rigid part of the single box. And what can I do? I can just model it with the grillage model. So the grillage model, what does is just technically divide this into smaller pieces. So instead of having one line, I have 4 line or 4 beams where they are connected with the transverse beams as well to make a grillage model for me. Alright, so this is also for this type of bridges. But this is not the end of the story, because there are possibilities, or there are projects similar to what Andrew introduced to us, where you have irregular shapes, you have a asymmetric geometry, and nothing works as you expect, or it's nothing is straight, it's not a real like a regular curves. So with this type of geometry, then what we have to do? As Andrew mentioned, so there are a couple of ways to handle this type of this type of geometry, or that was a solution that Andrew introduced. We can either use the beam elements, we can model it with the grillage model. We can also model them with the plate element. Each one has their limitations and also their advantages, which we're going to discuss about them today. So I got these slides from the Andrews, and as you can see, we have completely irregular shape, and we're going to see how we can treat this one. All right. The first method that Andrew introduced and he used was using a beam element, through the grillage model, where we have longitudinal elements like this. As you can see, these are the longitudinal beams, and also the transverse beams. So the way that he did it, he determined the node locations, then they created the element, and then the cross section, elements cross section. then created the element and assigned the the cross section for the transverse element as well. Then applying the load. So here we can apply the live load, dead load, post tensioning those elements, and then running different post tensioning tendons through different locations, and finally get the results. That was one approach. And the second approach that he followed was modeling it with the plate element. So in this model, I showed that what elements do we have in a real bridge, in a real project. They actually had different thickness of the slab in the bottom of this bridge, and as you can see, we have different thicknesses along this in some areas. So all of them should be modeled correctly, and as you can see, they modeled this with Midas Civil with the plate element, and when we model this with a plate element, then what we have to consider would be the importance of correct modeling for post tensioning. So in this model, we can simply run the post tension cables or strands and post tension them, get all the effects. In this way, when we have the plates, so we have to use some other skills to directly post tension the structure in the correct location. Okay. And finally, we can use the solid elements, depends on the project that we want, project that we have, and the output that we expect to receive. We can model the post-tension bridges with solid elements. So in Midas Civil, we have a tool that, for example, if you model the structure, model your box with the beam element, with the spline model, you can simply convert the model into solid by exporting them into Midas FEA. So you can see how the Midas FEA and Midas Civil works together hand in hand to provide you such a detailed analysis. Because what happened in post-tension bridges, sometimes you need to study a certain part of structure in very detail. For example, you may need to study those anchor blocks, or you want to study like other effects. You can simply model a certain part of structure or complete the complete bridge. You can model them in FEA, define those linear and non-linear, the time-dependent material properties which are non-linear, and also all the tendons defined through them. It could be modeled as a plate or solid, and then you can post-tension them easily and get the final result for them. And the good point about this conversion, when you can create this model in Civil, is very easy. It's 2 seconds. Then you can convert it into solid element and quickly mesh it. And also you can convert the tendon profile. So you can transfer the tendon profiles into Midas FEA and then combine them all together in the same model file, and everything is ready for you. So you don't need to spend additional time in Midas FEA to create the model. All right, the next week actually we're going to is the audio working? I received one query that someone cannot hear me. Can anyone else hear me? Could you please raise your hand one more time if you guys can hear me? I want to check the audio quickly. All right, thank you. All right, so that might be the problem with the user. All right, I'm sorry for that. All right, so so far we talked about the methods of modeling. Next week, I'm gonna show you how we can use Midas Civil for creating such a geometry, and whatever Andrew did, we're gonna show some case studies on his model. Gonna show you how we can quickly model that type of bridge or any irregular geometry that we have in Midas Civil. All right, so now let's talk about the analysis and design considerations as per H2O LRFT. Okay, So this is the general approach for the design of pre-stress and post-tension bridges and also segmentals as per H2LR-FD. I don't go into too much detail, just quickly touch base on some of the main categories that are provided or required by H2. Okay, so for the H2 requires us to do the design as per ultimate limit states and also serviceability limit states. So for the ultimate limit states, we have to satisfy the flexural resistance, shear resistance, and torsional resistance, and definitely combination of the shear and torsion. On the other hand, we have to check for serviceability limit states, checking the stress for the cross section at the construction stages. So that's definitely important at different ages. We have to also check the cracks or ultimate stresses before they pouring the concrete on top or after that. And principal stresses at construction stages, principal stress at service loads, all of them could be, must be checked for the post-tension bridges. So talking about each one, let's say about the ultimate limit state. For the flexural resistance, general term is always the capacity of the section should be larger than the demand that we have. So general term, Vmn should be larger than the ultimate force that we have at the sections. And depending on the the state of that segment, we come up with the different resistance factors. So as you can see, based on the ultimate strain that we have, so if the strain is less than the 0.02, which means it will be the compression control, so the concrete may fail initially, so we go with the smaller resistance factor. And when it comes to the goes to epsilon t is larger than 0.005, which means it could be a tension control. So we are using a larger resistance factor because we had more safety and more lesser probability there. All right. So finally, we have to get check the strength of the section or the capacity of the section. There are two main approaches for doing that. One is the code equations, which you can simply follow them. There are simple equations, and based on those, sometimes you need to do the iterative methods, but those are pretty simple and could be handled. And another method, which is more sophisticated, is the strength compatibility method, where we can use the actual stress strain material properties. So definitely you get better results when you do the strain compatibility. But to be in a safer side, you can follow the codes. So always the code equations are more conservative compared to the strain compatibility. But strain compatibility is also completely reliable and safe design. So you can simply follow that one too. All right, the next part for the ultimate limit states is the shear resistance. Again, the same terminology and the same equations. The factored shear at the section should be always smaller than the factored shear resistance. So we come up with this equation. V ultimate should be smaller than phi times Vn. And normally for the shear, we use the reduction factor of 0.9. Okay. And the code is actually providing you two different equations for segmental and non-segmental boxes for calculating the capacity of the sections, because we get the demand from the analysis. So regardless of the type of section, we can get those ultimate shears, all right? But for the shear resistance, we need to consider if it's a segmental or non-segmental. So as you can see, there are different as you can see, there are different methods of different equations provided. So this will be the minimum of each of these two. For example, for if it's non-segmental, it will be the minimum value of these two options. And another important factor would be the torsion, because we have to calculate the check the torsion separately, and also we have to see the effect of the torsion and shear at the same time to come up with a safe design. So next session also I will show you how Midas will provide you the detailed design sheet explaining all these steps for the ultimate limit state and you know, the serviceability limit state, all of them listed for you, all the you know, details provided, and we can simply check if you want to go follow the code or you want to follow the you know, equation from the strength compatibility method. All of them will be provided to you next week. Okay, so for the serviceability limit state also, we have to check the allowable stress of the concrete in different stages, because I mean, depends on the, when we jacking the post-tensioning tendons, it might initially cause a lot of stress or tensile stresses in the concrete, in the top of the concrete, and might cause it to break. So all of those should be checked during different construction stages. And in the segmental and post-tension bridges, we have to model different construction stages. So those also will be modeled for you next week on the, with the Midas Civil. We have to check the stresses for cross-sectional service load, as also tensile stress for pre-stressing tendon should be checked, both for the allowable stress and tendon losses. So about the tendon losses, I talk about the time-dependent properties, and when we have the post-tensioning, definitely the friction losses, and all those will be discussed. And also we have to check those crack check based on the equations that code provides. If you follow the spline model, those will be checked for you in Midas Civil, and definitely we have to do that. So coming back to the analysis requirement, we talked about the construction stages. So in the construction stages, what happens, we can define the different days and ages for the concrete, and we can see the different ages for the concrete at different stages of the construction. So technically we need to have some sort of time-dependent material property which affect the analysis, affect the results, and definitely the design, because we have to check let's say stresses at different stage of the construction. So how we have to do that? We have to define the time-dependent material properties for concrete itself, and also for the post-tensioning tendons. But let's see how those are defined and what are the effect of those. The first of them would be creep. So as you guys may know, the creep is the deformation of the concrete under permanent stress or permanent loads, which is in addition to the elastic deformation. So this happens when we have a large forces on the concrete. So concrete kind of like goes smaller, and what happens is releasing the actual load which was applied on that. Therefore, we come up with some sort of losses, which we call it creep loss. And how to define these creeps? There are several ways. You can get the creep coefficient curves from a actual test which has done, for example, in the universities, and then you can get those curves. But what you need for the design, you don't need to go that far. You can use either the equations that are provided by AASHTO, ACI, PCA, or also AASHTO led us to use some codes like CVFIP 1990, which is pretty decent and well accepted equations for them. So you can simply define that, and if you are using some software like Midas Civil, what happens at the different ages, different days, software takes different creep coefficients from this curve and then uses for the calculation, uses for calculating the losses, uses for calculating the the displacement of the structure at different stages. The same thing for the shrinkage. Shrinkage is also happening in the concrete due to dehydration. So what happens, the structure or beam shrinks a little bit because of the losing the water. So this effect also causes some additional losses in the tendon. So coming back to the basics of post-tensioning and pre-stressing thing is what is important for us. We are providing additional pre-stressing or post-tensioning forces in a way to give a let's say negative camber upward. Then it's gonna help the structure to carry the more load. Therefore, those post-tensioning forces that we apply is pretty important to maintain that force. So some effects like a creep and shrinkage causing to having the reduction in that level of the post-tensioning forces. So this is definitely important for us, and as you can see, these are the time dependent. So it means in a different ages they have different effects, and we have to be able to do all those calculations. So for example, in Midas Civil we can calculate that. We can give the get the result for different ages of the construction, and also as per Ph.D. code, it asks us to check the the formation of final losses at the age of 10,000 days. So all of them are could be effective to this structure. Another time-dependent effect of the time-dependent material property is the compressive strength of concrete. So the creep and shrinkage are normally have a long-term effects. As you can see, it goes to the 10,000 days and the curve changes. But when it comes to the compressive strength of concrete, we can consider it as a kind of short-term effect, because concrete after 28 days it carries a 98% or 97% of its strength. But what happens from day 0 that you are pouring the concrete until day 28, so definitely the compressive strength of concrete changes, and as the modulus of elasticity in the different codes are provided as a function of compressive strength of concrete, as you can see here. So I browse this from the ACI code. So you see that the modulus of elasticity is a function of the F prime C, or the compressive strength of concrete. So definitely when we have changes in the compressive strength of concrete, modulus of elasticity goes down, or changes. Now I can say it goes up and down, changes, and modulus of elasticity is a part of the stiffness that we define for bending stiffness for the for a beam. So definitely that gonna affect the deflection of the structure. All of them are important, so definitely we have to consider the this time-dependent effect as well. Another thing for another time-dependent effect is the tendon, the post-tensioning tendon itself, because what happens in the steel, we have one effect called relaxation, where the material itself just release some of those for initial forces that it has, and goes slightly just loses that initial effect by having a little bit of deformation. So to avoid that point, so code normally not requires, but ask us to use the low relaxation strand. So those are pretty helpful to come up with lesser relaxation loss. So all those effects like a creep and shrinkage, and relaxation loss, friction losses in post-tensioning, all of them will be added to each other. We have to consider them or calculate them for every single step of the design, and check the stresses, check the deformation, check the cracks, and to come up with the safe design. And again, don't forget, we know that code requires us to do all these checks up to the day 10,000, so we can do that for the final design. Okay. Another factor in the in the post-tension bridges is moving load. So this is another thing that the code requires us to consider. So if you remember, we said that we can go with the spline model, and based on that, code give us some load arrangement for the placing the tendon or the truck on the structure in a different position to find the maximum reactions, to find the negative moments in the support, and also the maximum moments in the interior mid spans. So these are the some of the load configuration and arrangement that the code asks us to do. For example, when you have interior support, code says that, all right, apply the two truck at two sides of this interior support with the minimum spacing of 50 and maximum 90 feet from each other to find out the maximum bending moment, negative bending moment in this support, and again for the support reaction. Alright, and then you can see the configuration in the transverse direction. So these are important. We can follow this arrangement and configuration, but in Midas Civil, you don't need to worry about them. You can just simply define your lanes, as you can see here, because in Midas, we are doing a 3D analysis. So you can, although you model them with the spline model, you can define different lanes with a different eccentricity, and define the load arrangement on the structure, and the software automatically applies different possibilities of the loading on the different lanes, and provides you the extreme result for both bending moment, negative bending moments, and also maximum bending moment, and all the deformations. All of them will be provided to you automatically. Another factor that we have when we have the segmental bridges, code asks us to run the transverse moving load also on that, which means we have to just take one segment out and then run the truck in the transverse direction to check the maximum and minimum effects. For example, here what we have, I modeled this bridge with the spline model in Midas Civil. This is what I showed you in the beginning of the presentation. It was just a spline model. And we can select one segment from here, and software automatically converts it to the 2D frame, and runs the vehicle on top of that, and provides me the maximum bending moments and the shears that different part of this segment may experience. So I can simply check the result for that one as well. Yeah, that's all I wanted to share with you for today. Just about the we studied the different methods of construction. We talked about the different method of modeling of post-tension bridges. We talked about the design requirements and what Ashto asked us to do, and then how to handle those. We talked about the time-dependent material effect on the design, and also we talked about the moving load analysis, and also transverse moving load analysis. So in the next session, I'm gonna show you how you can use Midas Civil to create such a geometry, like a complex geometry that Andrew presented us, and we just see the tools are available for us. And also, so in the next session, I'm gonna show you that one, plus showing you if you have a regular like a post-tension boxes, how you can handle that, and what tools that Midas Civil provides you for those. And also talking about the H2 LRFT design, and how Midas Civil completely give you a complete design sheet with all the steps for different part of the structure, and all the things which is available for, required for post-tension. So hopefully I can see you guys next session. It's gonna be next Wednesday. So please sign up for that. You'll probably receive the link. Otherwise, we're going to send it over to you guys. And you are more than welcome to join us there. I put this on mute now. And if you have any questions, please feel free to ask it now. I'll be so happy to answer the questions. Thank you and have a good day.